Well, hello. I will be walking you through the solutions to the questions from the third midterm. So if we look at this first question, it's Zinc 2 Plus, and so as we did in class, just do the configuration for just neutral zinc. And so if we look at the periodic table, zinc is here, and so it's going to be argon, 4s2, 3d10, because it's completely filled. Okay, and then when you're losing the two electrons, remember that the ones that get lost first are the s electrons. So it's just going to be argon, 3d10. Okay, nitrogen, ground state of nitrogen. It has a 1s2, 2s2, 2p3 configuration. And by Hund's rule, remember that those three electrons have to go in spin parallel first. And then if it was a p4, then you'd come in with one there, for instance, with the opposite spin. Okay, electronegativity. So this is just a definition that we talked about a lot in class. So it's just attracting electrons toward itself. This one, number of water molecules for this half reaction. So I think this one might have been exactly from the... No, I guess this is different. I was thinking it was from the practice midterm, but this is in a basic solution. So MnO4 minus goes to, and I think it's different. We just had Mn2 plus in the other practice exam, but it's similar concept. And so we balance the manganese first. Now we do the waters. So we've got 2 oxygens on the right, 4 on the left, so we need 2 waters. Okay, and so as far as the question, how many water molecules, you're done. Okay, there's 2. But just to show you the full balancing here, now we're going to need a 4H plus over here. Okay, and now the whole right side is neutral, and we've got something that's a 4 plus and a minus 1, so this is a plus 3 over here. So you're going to need 3 electrons on that side. Okay, so now it's completely balanced. In acidic solution, in basic, we just have to put in 4 hydroxides on both sides. So it really would be, this is 4 waters. And we've got 2 waters over here, so that leaves you a net 2. So the whole balanced in basic solution is 2 waters plus permanganate plus 3 electrons. Yes, gives you MnO2 plus 4 hydroxides. Okay, and so you'll notice that everything is still charge balanced, right? You've got a minus 4 over here and a minus 4 over here. Okay, so this will be the full balanced half reaction in a basic solution. It's again just asking for the water part. Oxidation state of phosphorus, so PO3, 3 minus. So you can set up a little equation. If you know that oxygen is going to be minus 2, and you have 3 of them, and you know that the overall has to be a minus 3 charge, then just let that equal x. Okay, so x minus 6 equals minus 3. So that means that x has to be plus 3. Ground state for cadmium. So cadmium is here, so it's going to be krypton. And then, what is that? 5s2, 4d10. Okay, so that one there. So it's krypton, and then you go 5s, and then you're filling all of the 4s. Ground state configuration for F minus, and so it's the same thing as neon. And so it's going to be 1s2, 2s2, 2p6. And selenium is down here, so it's going to be argon's configuration, 4s2, 3d10, and then it's 1, 2, 3, 4 for the p's. How many valence electrons do the halogens possess? So halogens are in this group, so it has 7 valence electrons. Okay, so in other words, fluorine, for instance, would be helium, 2s2, 2p5. These are the valence electrons, so there's 7 of them. Decreasing radius size. So an anion is always larger than the neutral species. Okay, and if something has a multiple negative charge, that would be larger yet. Okay, so for instance, like nitrogen is smaller than N minus, that's N2 minus, and then N3 minus would be the largest. Okay. Isoelectronic, we did examples in class. This means the same number of electrons as something. And so P3 minus, whoops, I haven't had it on the, oh, great. If I go back, I had it still in the periodic table. Where were we? Right here, I think, for this one. So valence electrons for halogens. So halogens are in group 17. And so this is the electronic configuration for fluorine. So you have 7 valence electrons, 2s and the 2p are the valence. This is the one I was blah-blahing about, but I didn't show the screen. So the more negative charge a species is, the larger it's going to be. So this would be larger than that, would be larger than that, and larger than that. So this is the only one that makes sense. And likewise, cations are always going to be smaller, so that should be a negative sign than the neutral species. Okay, so here we go. So isoelectronic, same number of electrons. So P3 minus, 1, 2, 3, is the same as argon. Okay, and other options you have is an S2 minus. That's also argon. Cl minus and K plus. K plus is argon. Cl minus is argon. And calcium 2 plus. If you lose 2 electrons from calcium, you're also at 18, which is argon. Okay, so all those are isoelectronic. Whereas if you look at some of these others, like N3 minus would be neon's configuration. S2 minus is argon's configuration, so that's not the same, okay, etc. This one, just definition, that's what a p orbital looks like. We showed that in class, and it's along the x-axis, so that's px. Reducing agent means the species that is being oxidized, right? So iron goes to iron 2 plus, so that means iron is the reducing agent. The reducing agent is the one that's being oxidized again. And so it'll be cadmium going to cadmium 2 plus. Okay, so it's being oxidized, so cadmium is a reducing agent. Which is the oxidation state of hydrogen not +1? It's this example that I think I went through the lecture just before the midterm. So all of these, since hydrogen is on the left side of the more electronegative species, you can just assume hydrogen is +1. In this case, sodium is always plus, and so hydrogen can't be +1. It has to be -1. Okay. Decreasing first ionization energy. Okay, so remember that ionization energy, i.e., increases as you go left to right, and it decreases as you go top to bottom of a group. Okay, so here we've got argon, magnesium, and cesium. So argon is here, magnesium is there, cesium is there. And so cesium is going to have the lowest ionization energy. Okay, so you're looking for something, I guess it boils down to these two. And then it's really between argon and magnesium. And again, as I showed here, it increases as you go left to right. And so between magnesium and argon is going to have the highest. Okay, so argon highest, magnesium, and then cesium the lowest. So shortest to longest wavelength. So remember that energy is inversely proportional to wavelength. And so we're really going, if it's going to longest wavelength, that means it's to lowest energy. And so radio, whoops, I just lost connection here. So radio waves are the lowest energy radiation, and so that's going to have the longest wavelength. And then gamma rays are the highest energy, so it's going to have the the shortest wavelength, the largest frequency it would be. And so then this is the order, so it's gamma, UV, and then we've got visible in between here, and then infrared and radio. Microwave is in between here. Okay, so it just was based on kind of memorizing the EM spectrum. Okay, calculation. We want to know the wavelength if you're given the frequency. And so C is wavelength times frequency. That means wavelength is C divided by nu. And you're given everything you need here. Meters per second. And you're given this frequency in terms of megahertz. Okay, so 99.1 megahertz. And we want to know it in terms of hertz, or reciprocal seconds. So we'll just do it like this. Okay, so a megahertz is 1 times 10 to the 6th hertz, because remember it's a kilohertz, and then a mega is another factor of 1,000 greater. And so we really have, I know this isn't proper scientific notation, but you can do it like this. Okay, so the seconds to the -1, or that's hertz, they cancel. Okay, and so we end up with 3 times 10 to the 8th. If I do it in the calculator here, 3 e to the 8th, and then divide it by 99.1 e to the 6th. And so we have 3.03, and the units are meters. Activity series, and so the higher up it is, the more that it is preferred to be oxidized. So that means between magnesium and zinc, magnesium is going to be oxidized because it's higher. And then between zinc and copper, zinc is going to be oxidized because it's higher. Okay, if we look at the other situations, this would imply that magnesium is higher than copper, which it is. But this one, you've got 2 plus species, so that means that both are going to be reduced, so that doesn't make sense. This one, you've got two metals, so both are going to be oxidized, so that doesn't make sense, and same with this. And then this one, this is implying that copper is higher than zinc, and that's not the case. And this one is implying zinc is higher than magnesium, and that's again not the case. Okay. N equals 3. Whoops. N equals 3, so that means L can take values of 0, 1, and 2. And so if you remember, that's an S, that's a P, and that's a D orbital. Oxidation, so zinc is going to Zinc 2 Plus, so that is oxidation. This is just definition, so distance between identical points there and there is a wavelength. Oxidation half reaction. Okay, so this is the full redox. If we're looking at this is a -1 charge, this is a 0, so that means oxidation. Okay, and so it's really just this. So Cl- goes to Cl2. Whoops, what am I doing? Cl2. Okay, and then balancing. It's a 2 there. And then we need to do for charge. So there's a -2 over here, so you have to do it -2 as far as electrons. So that's your balanced half reaction. Oxidation number for sulfur. So this whole thing has to equal 0 because it's neutral. And so again, you can do kind of your little math. So we have each hydrogen is 1, and so there's 2 of them, plus X, we don't know what sulfur is, plus 4 times a -2. That all equals 0. So you've got 2 plus X minus 8 is equal to 0. So this has to equal +6. And then this one, S8, I did an example on the board saying that all elements, including all the allotropes, are 0. So that would be 0. This is like the previous question, so now you're given frequency, so it's just frequency is C over wavelength, so 3 times 10 to the 8th meters per second. And now you're given 4.8 times 10 to the 14th seconds to the -1, so those go away. And so you get 3e to the 8th by 4.8 e to the 14th. So you get 6.25 times 10 to the -7 meters. And all these answers are in terms of nanometers, so we have to convert that to nanometers. And so 1 meter, we'll say, we'll do it this way, is a whole bunch of nanometers. Okay, so that times 1e to the 9th is 625 nanometers. Or I guess, closest, rounding up to 2 sig figs, I guess, is 630. Degenerate orbitals. So we looked at an example of this earlier for the nitrogen configuration, where they all go in with parallel spins first. This is Hund's rule. Talked about that in class a number of times. Which element is reduced? So copper goes from copper 0 to copper 2 plus, so that's being oxidized. And so what's being reduced is the sulfur. We saw in an earlier question that's a +6. The sulfur here is +4, right? Because oxygen -2 times 2 is -4, so that has to be +4. Okay, so that's going +6 to +4 is reduced. Isoelectronic Series. So that means the same number of electrons correctly arranged in increasing radius. Okay, so Cl minus, so anything negatively charged is going to be the largest. And then anything that's positively charged is going to be the smallest. And so this is the proper order here. So something that would be like 3 plus would be over here yet. Like let's say, I don't know, it doesn't form it, but like, well, actually let's do a real one. Aluminum, 3 plus, would be even smaller. Okay. Electron affinities, this is just a definition, so it means picking up an electron. And then the last question, a reducing agent, that means it's being oxidized. And so phosphorus is going to phosphorus 3 plus, so that means that's the reducing agent. All right, so hopefully that helps. Let me know if you have any other questions.